Beyond high-speed rail, a new vision takes flight.
Indian Railways is a giant. For over a century, it has been the backbone of the country's transport, moving millions of people daily on an immense steel network. But steel on steel has strict physical limits. With a booming population, the system is straining under sheer volume, maxing out what conventional rails can handle safely and efficiently. Passengers who can afford it are migrating to luxury buses and domestic flights. That migration is clogging highways and pushing airports closer to their absolute saturation point. Adding a few more tracks or squeezing out slightly higher speeds won't solve the congestion. The country requires a complete technological jump to keep moving. That jump means abandoning the wheel entirely. By lifting a train off the ground, you remove the mechanical friction that holds traditional rolling stock back. This is magnetic levitation, or MAGLEV. It uses powerful electromagnetic forces to suspend and propel vehicles a few centimeters above a specialized guideway. Without the drag of physical contact, these trains can hit 500 to 600 kilometers per hour. That speed makes ground transport a viable, direct competitor to regional air travel. Stripping away friction creates a smoother, highly stable ride that actually uses energy more efficiently at extreme velocities. One of the primary ways this works is through electrodynamic suspension, or EDS. Strong magnetic fields push away from the track, lifting the vehicle into the air through pure repulsive force. Once hovering, the train needs to move forward. Instead of a spinning engine turning an axle, it uses a linear induction motor, essentially an electric motor unrolled flat along the guideway. The guiding walls contain magnetic coils with alternating north and south poles. These pull the train forward and push it from behind. Computers rapidly switch these polarities along the track, creating a continuous wave of momentum pulling the train. Because there is no mechanical contact, the whole process is virtually silent from the inside, and the components suffer almost zero physical wear and tear over decades of use. The Indian government is actively pursuing this. The Ministry of Railways has issued an expression of interest to bring maglev technology to the subcontinent. The rollout strategy is cautious. The chosen contractor must first prove the technology works on a 10 to 15 kilometer test track before laying down a 200 to 500 kilometer elevated guideway. 4 high-density routes have already been shortlisted for this infrastructure, including the high-traffic corridors between New Delhi and Chandigarh and Bengaluru and Chennai. Building this requires immense capital, which is why the completed system will operate under a public-private partnership. This structure helps distribute the massive financial risk away from the government alone. Maglev trains cannot run on conventional steel rails. Adopting this technology means buying into a completely closed ecosystem, requiring entirely new tracks and stations built from scratch. To generate enough magnetic force to lift a heavy passenger vehicle, the system relies on superconducting magnets. But these materials only work when kept below extremely cold critical temperatures. Keeping them cold requires continuous, highly demanding cryogenic cooling systems, often using liquid nitrogen or helium, that must remain stable across hundreds of kilometers of track. If a magnet warming up and suddenly loses its superconductivity, an event known as quenching, the levitation can destabilize, creating a major safety hazard at 500 kilometers per hour. This situation creates a difficult engineering paradox. The energy you save by eliminating the mechanical friction of wheels is often eaten up by the immense electrical demands of those cooling systems. This visualization shows the high energy costs of cryogenic cooling on the left against the massive electricity demands of propulsion on the right. That heavy energy draw makes initial construction tremendously expensive, even if the lack of friction saves money on long-term track maintenance. Because of these high barriers, only a handful of nations have managed to deploy large-scale maglev systems after decades of intense research and development. Germany's pioneering Transrapid project, for instance, faced immense public resistance over its high costs, and now operates entirely outside its home country. Importing this technology costs upwards of 400 crore rupees per kilometer. For India to make this viable, the country will have to develop the technology indigenously, driving down the unit economics. If they succeed, it solves a critical capacity crisis while making high-speed travel dramatically more comfortable. It's a massive gamble, but one that could push this technology from a niche marvel to the standard for global mass transit.